Chapter 11 in the Abstract Algebra series is on equivalence relations, and problem number 1 asks us to draw the arrow diagram to the given relation. And notice that in the set of ordered pairs here, notice that 1 maps to 1, and 1 also maps to 2, and then 2 maps to 1. So that's all we have on that set to work with. So let's do the arrow diagram. Well, let's talk about the arrow diagram since it's already completed. Notice that we have an arrow here pointing 1 back to 1, which satisfies this first ordered pair. And notice that we have 2 arrows pointing in the opposite direction. One shows that 1 is mapping to 2, and then the other arrow shows us that 2 maps to 1, and that satisfies the second ordered pair and the third ordered pair. Number 2. Number 2 says to add the minimum number of arrows to your answer for number 1 so that the represented relation is reflexive, meaning that each element relates to itself. In order to have a relation that's reflexive, every element has to relate to itself. And we were given in number 1 that 1 relates to itself. But in order to make it reflexive, we would also have to force 2 to relate to itself, and we would have to force 3 to relate to itself. Number 3. Number 3 says to add the minimum number of arrows to your answer for number 2 so that the represented relation is symmetric. Well, a relation is symmetric if the following principle holds. If A relates to B, then B would have to relate to A. Okay. If we go back and look at number 2, do we have the initial condition satisfied for any 2 elements? Well, we do, because we know that 1 maps to 2, and then 2 maps to 1. So this diagram here already shows a symmetric relationship, because this is a conditional statement, and the conditional statement says if A relates to B, then B relates to A. And since we had 1 mapping to 2 and 2 mapping to 1, then that condition was satisfied. Also, notice that 3 maps to 3, so we could say if 3 maps to 3, then 3 maps to 3. So again, the condition is met for those elements. Number 4. Number 4 says to add the minimum number of arrows to your answer in number 3 so that the represented relation is transitive. What is the partition to this equivalence relation? Well, again, remember that we're working with conditional properties, and a transitive relation works like this. If A relates to B, and B relates to C, then A has to relate to C. So let's go back and see if the hypothesis is satisfied in the arrow diagram in number 2. Do we have an A relating to B and a B relating to C? Well, we have 1 mapping to 2 and 2 maps to 1, and therefore 1 maps to 1, which means that we have a transitive relationship between 1 and 2. We could also say the same thing about element 3, because if 3 relates to 3 and 3 relates to 3, then 3 relates to 3. Seems somewhat redundant, but that is how we do. That's how we test these relationships. Let's talk about the partition. What is the partition to this equivalence relation? Well, the condition would be the set that contains subsets that tell us what's going on between the elements. And since 1 maps to 2 and 2 maps to 1, remember in sets, order does not matter. And I generally write my sets with the smallest element first. So this lets me know that 1 and 2 are working together, or mapping to one another. And this set here that contains only 3, this tells me that 3 only maps to itself. Remember, a partition breaks a set into disjoint subsets. In other words, the subsets do not have an element in common. And if you look at the set containing 1 and 2, and then the set containing 3, those are disjoint sets. They also have to be non-empty sets, which they are. And the union of the subsets has to be the whole set. Well, if you take the union of the set containing 1, 2, and the set containing 3, then you get a set containing 1, 2, and 3, which is the whole set. Number 5, let R be a relation of the integers defined by A relates to B if and only if A minus B is even, and is the relation reflexive, symmetric, transitive. So we'll answer all of those questions after we sort of take a look and see what's going on with this particular relation. First of all, we know that the relation involves the integers. So we do have a restriction there. And we know that if we take any integer, any ordered pair that consists of integers, and we take the first element and subtract the second element, we have to get an even number, an even integer. So that's the relation for any ordered pair. And the first question is, would this be reflexive? Reflexive, if you'll recall, means that A would have to relate to A. In other words, A relates to itself. For example, if you take the integer 2, would the integer 2 relate to 2? Well, 2 minus 2 is equal to 0. And 0 can be written as 2 times 0, which means 0 is an even integer. Now that only holds for the ordered pair 2, 2. We have to show that it holds for all ordered pairs A, A. Well, A minus A is equal to 0. And again, 0 is an even integer. So we do have the reflexive property for this given relation. What about the symmetric property? Well, the symmetric property is satisfied if we can show that if A relates to B, then B relates to A. Well, if the former is true, in other words, if A relates to B, then that means that A minus B is even. So we must show that that leads us to B minus A being an even integer. Well, B minus A is minus A minus B. And that too would be even. For example, if m is a multiple of 2, in other words, if m is even, then minus m, right? Negative m is a multiple of 2. So we have just shown that this relation is symmetric for any ordered pair AB. Finally, we must satisfy the transitive property. And we will satisfy this without a lot of mathematical rigor. Let's just say that if the distance between any two integers A and B is even, and the distance between integers B and C is even, then the distance between integers A and C would have to be even, because the sum of two even distances would give us another even distance. So the transitive property also holds. And just as an aside, I could make the case that if we wanted to partition the sets, we could partition those into the set of even integers and the set of odd integers, because if you take any two elements from the set of even integers and subtract them, you're going to get an even number. And likewise, if you take any two elements from the set of odd integers and you subtract those, you are going to get an even integer. Number 6. Number 6 says, let R be a relation on the set of people defined by A relates to B if and only if A and B are born within 1 day of each other. And would this be an equivalence relation? You have an equivalence relation if the relation is reflexive, symmetric, and transitive. Well, the transitive property would fail, for example, if in the same year, let's say that I was born on March the 13th, and you were born on March the 14th, and let's say Socrates was born on March the 15th in the same year. Well, I would relate to you because we are within a day of one another. And you and Socrates would relate to each other because you are also born within a day of each other. But the problem is me and Socrates, because Socrates and I would have a 2-day gap between our days of birth. So the reflexive and symmetric properties would hold, because obviously I am born within a day of myself. That takes care of the reflexive property. And of course, if I am born within 1 day of you, then you are born within 1 day of me, so that takes care of the symmetric property. So the issue there is with the transitive property. Number 7, let R be a relation on the integers defined by A relates to B if and only if the product of A and B is non-negative, greater than or equal to 0. Is this an equivalence relation? Well, again, in order to be an equivalence relation, the relation would have to be reflexive, symmetric, and transitive. But we have a problem here, and the problem, again, is with the transitive property. It's enough to show, for example, that if A happens to be positive and B is equal to 0, well, that would give you a positive integer times 0, which is 0. That meets the condition. But suppose C is negative. Well, if C is negative, then the transitive property fails. For example, if A relates to B, let's say 3 relates to 0, because if you multiply 3 and 0, you get 0, which is greater than or equal to 0. So this would be A relates to B, and here B relates to C, where C is negative 2. But the problem is that A does not relate to C, because if you multiply 3 times negative 2, you get negative 6, which is not greater than or equal to 0. Number 8, let R be the relation on the integers defined by A relates to B if and only if A and B have the same remainder when divided by 3. Describe the equivalence classes for this relation. Well, any integer when divided by 3 is going to have a remainder of either 0, 1, or 2. So any integer you pick, if divided by 3, is going to fall into this class. I'm going to call that the 0 class, or the 1 class, or the 2 class. For example, let's pick 7. Well, if you divide 7 by 3, you get a remainder of 1. So 7 would go into this 1 class. Same thing with 10. If you divide 10 by 3, you get a remainder of 1. It would also be in the 1 class. And I could just keep adding and subtracting 3 to these numbers, and I would continue to get numbers that fit into the 1 class. If you have an integer that's a multiple of 3, either positive or negative, then it would go into the 0 class. For example, 3 divided by 3 has a remainder of 0, so 3 would be in the 0 class. 6, if you divide by 3, has a remainder of 0. It would go into the 0 class. And as before, I can just keep adding and subtracting 3 to these numbers to generate a set that would go into the 0 class. What about 8? If you take 8 and divide by 3, you have a remainder of 2. So 8 would go in the 2 class, along with 11 and 14 and so on. So all of the integers would go into one of these classes, the 0 class, the 1 class, or the 2 class. In other words, we can partition all of the integers and zip them up, so to speak, and place them in one of these 3 categories. Number 9. On problem number 9, it says to list all of the partitions of the set containing 1 and 2. Well, remember that partitions have to be non-empty sets, and the sets within those sets have to be disjoint, and the union of the sets must encompass the entire set itself. And of course, we do not have a very, very big set here. We only have the elements 1 and 2. But this is one partition. You could partition the set 1, 2 into 2 sets. One is the set containing 1, the other is the set containing 2. Notice that these are non-empty, they are disjoint. And if you take the union of the 2 sets, you would get the entire set. And of course, we could keep 1 and 2 together like this, and that would give us a non-empty subset, or a non-empty set rather. And of course, it's vacuously true that it is disjoint, and it is already the entire set. So these are the 2 partitions that you can make from the set containing 1 and 2. Number 10, what is the equivalence relation? In other words, give its set of ordered pairs. What is the equivalence relation that corresponds to the following partition? So we took the integers 1, 2, 3, 4, 5, and 6, and we have partitioned those in this manner. We have one set that contains 1 and 2. We have a set that just contains 3. And finally, we have a set that contains 4, 5, and 6. So what would the set of ordered pairs look like for this particular partition? Well, notice that 1 relates to 2, and 2 relates to 1. That would take care of this set of ordered pairs. And also, 1 relates to 1, and 2 relates to 2. How do I know that? Because if you can partition a set, then that means the set is an equivalence relation, which means that the reflexive property has to hold. So 1 would have to go with 1, and 2 would have to go with 2. Also, the symmetric property would have to hold, which means that if 1 relates to 2, then 2 would have to relate back to 1. And the transitive property happens to work by default. You can check that on your own. And of course, 3 just relates to 3, and that satisfies the reflexive, the symmetric, and transitive properties. If we go to the last set here, we know that each element has to relate to itself. So 4 would map with 4, 5 with 5, and 6 with 6. And we know that because of the symmetric property, if 4 relates to 5, then 5 would have to relate back to 4. And if 4 relates to 6, then 6 has to relate to 4. If 5 relates to 6, then 6 relates to 5. And of course, the transitive property is satisfied as well. What does this mean? This means that if you examine the given partition, it means that there is some relation out there. There's some criteria that has been defined that is satisfied by these ordered pairs. All of these ordered pairs satisfy some criteria, some relation.